All right, so let's start. Thank you all for coming. This is a tutorial on Python for linguistic data analysis. I was really scared of writing NLP up front. So it's just language, and if you want to work with language and use Python, you're at the right place. Who am I? I am a data scientist at Moz. I have a background in computer science. I did my bachelor's, master's, and PhD in NLP. My PhD was in NLP, and everything else is computer science. And I worked on a lot of cool projects like IBM Watson. I've used NLP for healthcare. Right now, I'm working on SEO, that's search engine optimization at Moz. I've also done sentiment analysis, question answering, natural language understanding, and a bunch of other things. So before we start the tutorial, I kind of wanted to put forward a few goals. I want to make this extremely interactive. So if I'm going too fast or too slow, or if there's something you just don't understand, just feel free to stop me and ask me a question. No question is silly. In my experience, what I've felt is that if I have a question, 5 other people also have that question, but it's helpful when one person asks because there are 4 other people who say, yeah, me too. We'll code as we go. So if you want to install IPython, I think that's the main requirement. There's also a repo with some code, so it'll be useful if you have that repo forked. And the tools are right here. It'll be useful if you download or fork this repo, download it as a zip. There are just a couple Python files which have most of the code, but you can run it on your machine and see how it works. Some other tools, yes. All right, I'll wait a second till everybody has the link. Are we good? All right. Couple other things which you might already have. Install requests if you want to do some web requests and get some data. I've used Beautiful Soup in this tutorial to parse HTML pages, and also Gensim, and that's only if you want to use Word2Vec, which is another thing that I am going to give you a demo of. But before going into everything, quick poll, how many of us are familiar with Python? Excellent. How about NLP? Okay, some, that's pretty good. How about machine learning? Wow, quite a few, okay. And the last question is, what do you want to do with NLP? So if I could just get a few ideas of what somebody wants to do with NLP for when you takeaways from this talk, what would you like to do?
Quantify qualitative data.
Okay.
So like specifically like reviews, or if we have user experience research, stuff like that, just turning it into numbers that we can process.
Okay, quantify qualitative data like reviews.
Cluster unstructured data.
Cluster unstructured data. Okay, all right.
Sentiment analysis.
Sentiment analysis, all right. Extract information and give it to an ontology. That's a great one. Topic analysis is another one. Great, all right. So today I'm going to do quite a few basics of these technologies. We might not get to all of them, but hopefully it'll give you a foundation to understand how to work with linguistic data. So to start, I wanted to highlight a few areas of NLP. The sentiment analysis seems to be a big one. Given product reviews, how do we identify concepts that's like something like screen resolution, and then modifiers of that concept that says sharp screen resolution? And then once we get a concept and a modifier, we have to identify whether it's a positive sentiment or a negative sentiment. A sharp tongue is really negative, but a sharp screen resolution, that's awesome. So how do we do that? It changes with the domain. Similar with low battery life, low voice is good, but low battery life, not that much. Other things that have been done, there's text summarization. You have this long newspaper article, but you'll get what the newspaper article is about in the first 2 or 3 lines. And there are things like these automatic sentiment recognizers, like Sumly, which was acquired by Yahoo a few years ago, which does exactly that. You give it a large a piece of text, which could be a blog or a newspaper article, and it'll just tell you which pieces of that are key, are important. Then there's this Google Translate, which wasn't there 10 years ago or maybe more, because before this it was really hard to translate from one language to the other. Now we can take our smartphones, say something to it, and the smartphone will say the translated version in some other language, so which is pretty cool. So machine translation. Question answering, IBM Watson. It participated in Jeopardy and it won against 2 humans, which is pretty cool. This system is not only question answering, because it's understanding the question and then parsing it and then producing the right answer. And it's pretty similar to Siri, which we all have in our back pockets now, which does all of this stuff and more. It just in the NLP realm, it's extracting information, it's modeling it, it's clustering it, you name it. But it's not perfect. I found so many examples. Do not wake me up in the morning, and it doesn't understand negation. It says, okay, alarm is on. And then there's this other thing about, you need to start understanding me, Siri. I'll make a note of that. Yeah, make a note of that. Okay, of that, that's the note. So there are still a lot of issues with NLP. And one of the things that I feel is that going into NLP, it's always tempting to apply really cool algorithms, really cool technologies to get the most bang for the buck, but often we don't know what's behind the scenes. And one of the things that I want to do here is kind of get into the nitty-gritty and the basics, and just to understand why we should use the technology and why we shouldn't, and what goes on behind the whole phrase of NLP. So in this talk, I'm going to do 3 things. The first is information extraction, which is extracting stuff from unstructured data. That stuff could be anything, but if you know what information you want to extract. Whoa, what happened to my screen here? Okay, if you know what information you want to extract, you can extract topics, you can extract sentiment, you can extract named entities. The second is information retrieval, which is actually search, which is Google. It retrieves documents for you. The third, which is a demo that I'll do, is deep learning, which is picking up a lot these days, and it is not as intimidating as it sounds. We will just work with word2vec and see how words are converted into vectors and how we can do some kind of a vector manipulation with those words. So, I will pepper the talks with NLP folk knowledge, and it's your fairy godmother. So that's like somebody is telling you good things while you're coding your NLP stuff, and it's just folk knowledge which you usually don't find in a lot of textbooks. All right, let's start. If my slide will go forward. All right. You have just been offered a job at an innovative new startup in Seattle called New Tech Stories. So they come up with new tech stories. You have accepted this position and you're going to work with linguistic data. Awesome, congratulations, welcome aboard. Here's this data, analyze it. And that's the GitHub repo that I was talking to you about. It has this folder called data collection, and within that there is this file, data_file.txt, which has all the talks for PyData Seattle. And they're just 77, so it's not a lot of data, but it's enough to kind of get an idea of the talks here. Now, what the company wants to know is, what are people talking about? What is the trend in Python and data science in Seattle these days? Now, before we go to answer these questions, the fairy godmother comes and tells you, always know how to evaluate your data. If you're working with this kind of data, you should know what you expect to find. If you know what you should expect, like for PyData Seattle, you know that you expect that you will not find anything related to, say, garlic or onions or anything that's related to cooking. It's very, very unlikely. Also, you should have some kind of an idea about how to get there. So, for instance, if most of the talks, which are really popular, are all keynote presentations, is that possible? Or all of them are scheduled in room 1? That kind of helps analyze the data in a very intuitive way and helps you understand that, oh, I don't need really complicated machine learning or NLP systems on it. I can just derive it heuristically. So now that you know You've probably looked at the PyData Seattle talks a lot. Any ideas about what we expect to see? Data, yeah. Yep. I couldn't hear that. Machine learning.
NLP analysis.
NLP analysis. Tutorials.
Anaconda.
All right, I'm running out of room, so I'll just leave it to that. This is awesome. Now, one of the things I want to point out is that you guys said machine learning as opposed to machine and learning as two different words. This is a classic example of a bigram that's two words connected together. When we usually tokenize text, we have it as one word, and then we have to do some kind of post-processing to join these words together. And that post-processing is usually with some kind of statistics. So we see machine learning together all the time, but we don't see data machine together all the time. So that's a frequency analysis that we'll do. In this talk, I'll assume that we are only working with unigrams. That's a single word or a single token. And I'll leave the post-processing for future work. All right. On suggestions on where do we start? Now that we know that these are the keywords, how do we start looking at the data? What would be the first thing that you would do? Frequency. All right. TF-IDF. Is anybody familiar with TF-IDF? Yeah. Few. Very few. OK. What else?
LSI.
LSI. All right. Somebody knows their NLP really well. Word to vec. And if you were to do something more intuitive, what would you do?
Counting.
That's the frequency. I'm sorry? Categories. OK. In this tutorial, we'll do word frequencies, TF-IDF, and one of the things that nobody talked about, which is what if we use noun phrases only? And that's one of the things that I want to point out as an NLP person, that we often do not focus on the linguistics of things. There are parts of speech that we learned in college, in school, actually, that there are nouns and there are verbs. And in this particular context, if you're interested in instances of things, if the things that we are interested in are data and Python, machine learning, NLP, there aren't any verbs in here. There aren't any adjectives in here. It's all nouns. Maybe we can just focus on that and completely reduce our search space to something really, really small. All right, so if somebody has not downloaded the repo, I will just show you what the data looks like. All right, so it's JSON files, one JSON file per line, and in order to extract this, the code is actually in the GitHub repo if you look at it. But a few things that one has to take into account is the coding of these. Often you'll find issues with UTF-8, ASCII, Unicode. It's good to get everything into the same code type. I like string, UTF-8. And there's this module called UniDecode that decodes all of these special characters into strings. So that's NLP. One of the best friends of NLP, have everything in the same format, because you don't want funky characters in your text. The other thing that you will notice here is that the text looks, it's JSON, so it's easy to parse. And I've gotten all the data, so there's 79 lines. I usually like to code with IPython just because it's super interactive, and then we can figure out what's going on in smaller snippets of code as opposed to running it together. So for this particular experiment, we'll do word frequencies and figure out which is the most frequent one. If you have, how many of you have actually downloaded the repo? Okay, a lot of people. How many are actually trying to implement this? Okay, awesome. So if you go to the function, the file NLP tools and the function word count, you need to provide the text and the dictionary. So the input function that you should look at is NLP tools.information extraction, which is this file right here. So what this does is it imports JSON, which you need to parse that file. It has this word count, and it will parse through the file, compute the word count. In this case, it's also doing TF and IDF and all of these other things. But let's just worry about word count for now. It returns word count, which is what we're interested in. All right, I just pasted the whole piece of code into IPython because I know it should work. All right, so I have the word counts, and if I do the top 10 word counts, or all the word counts. Oh, I'm sorry, I haven't sorted this yet. So right now it's returning a default dictionary, which is, how many of us are familiar with default dictionaries? Okay, this is a great tool actually. If you haven't initialized a dictionary and you want to initialize it every time you see a word, use default dictionary. What I'm doing in this piece of code is I am for each line in this file, and let me open the file right here. For each line in the file, I load it into a JSON module called current, and I normalize it, normalize the abstract, the description, and the title, because those are most likely the things that we're interested in. We probably won't find anything in time, which is also a part of the actual text. Normalizing is a huge piece in NLP. I talked about UniDecode, which converts text to UTF-8. I also lowercase everything, so we don't want anything to be very case sensitive. We'll get multiple representations of that. And we also want to remove special characters. That's one of the things that totally eats a lot of extra space. So we get things like the word followed by the period to be a token, which we don't want it to be. It just adds a lot of noise to it, to the text. Once we normalize it, I have this function called word count. You provide the text and this default dictionary, which again is something that I will cover right here. Word count, it updates the default dictionary irrespective of checking whether the token is in the dictionary or not. So even if there's no token, by default it assigns a value to it. So you don't have to do that check every time, and you can save up on a lot of memory. So now that you've run this code, is it too confusing to run the code? Yes? All right. Would it be easier if I slow down a little bit and show you how to run the code? Okay. All right, so let's do that then. We're interested in the function information extraction because it takes in a file and it produces some numbers from it. And I have changed the code, I have updated the code with some suggestions from the audience that things like TF-IDF and document frequency. We don't care about it right now, but I will get to that in the next few minutes. For now, if you do not care about that, let's just remove that. All right, so this is like a very minimal piece of code. It takes in a file. It initializes a word count dictionary, which is an empty dictionary with value as integer. You open the file. You keep counting how many files, how many lines of code you're seeing so that you have the index of the document. For each line, you have the text. You pick up the pieces of text that are interesting to you, which is the abstract, description, and title, and then you count the number of words. Does that make sense? Okay, I see a few nods. Okay, now that I get the word count, it's in a dictionary which is not quite sorted, so I'll have to sort it first.
The text bigger, please.
Yes. Is it better?
Yes.
So here I've just written a lambda function which keys by the first value, which is the value of the hash rather than the key. And I'm sorting the items and I want to reverse it. That means I want it to go in descending order as opposed to ascending order. All right, so this is what we get based on frequency. Can everybody see the screen okay now? Should I still make it larger? Yes. Let me just keep it low. All right, so this was the first idea we had to do it based on frequency. And what are your thoughts? A lot of noise, yes. What is the noise? Can somebody speak up a little bit? I can't hear. Stop words, okay. All right, so what are stop words? A lot of common words, okay. So thank you for bringing that up. So there are a lot of stop words. What else can we see?
Contractions have been separated.
I'm sorry?
Contractions have been separated. LL 52, I'm assuming. I don't know if it's put on a
Yeah, and that'll be the case for sure. This is one of the things that we get for removing special characters and replacing it with space. Unless you have a post processor that merges together words or characters that should be together, like in this particular case, you will get that kind of noise in the data. But yes, absolutely valid point. So that kind of brings me to what I prepared in my slides actually, that we have words like and the, which are really common, but we shouldn't have them. And these are stop words. Something about stop words. Something about stop words. These are very frequent, don't add any value, and there is no real list of stop words. All right, my slides weren't moving. So they don't add any value to our data, and the interesting thing is that stop words are different for different kinds of domains. So in this particular domain, we are working with talks about PyData Seattle. What do you think are stop words here? Apart from words like the, off, what other words do you think are so frequent that we should just throw them out? Python and data, yeah, we'll see them everywhere, and they don't add any value to it because this is such a niche topic, and everybody's talking about these. So what a lot of people do is that they have their own list of stop words. In that case, they have common words like the and of, but they also add words that are really common in their specific domain. So for instance, if you're working with genes and proteins in some PubMed kind of data, you would want to throw those words out as stop word. All right. In this particular context, I have this file called stopwords.txt. And all you have to do is in your word count function, make sure that you check for stop words. And if you have a token that is a stop word, throw it out. If it's not a stop word, then keep it in. So let's go back to the code. Can everybody see the screen? All right. This is what we're interested in, word count. So far, we were taking in text, tokenizing it, so that's splitting it by space. And for each token, we were adding one to the dictionary. So if we see Python, we add one to that Python dictionary. Now we want to check whether that is a stop word or not. So first we will load the stop words. I have this load stop word function which does nothing but just adds to a set of stop words, adds tokens to a stop word. So we will have this set called stop words. And I choose set as opposed to dictionary just because the order of getting that value is 1. So it's better than using a list. How many people have used IPython before? Okay, so one of the functions that I'm using is the magic function paste, which makes sure that the indentation that you've used reflects in the terminal window. So instead of copying and pasting, it's nice to use percentage paste to paste that specific function. So I loaded stop words here. If I type stop words, then it'll give me a list of stop words. It's just these common words like yes, yet, you, you'll. I haven't removed special characters from here. I've just used a very standard template of stop words. So it might not remove everything, but it'll probably get most of the things that we want to remove. Any questions so far? Okay. So the next step is to modify the word count function such that it'll remove the stop words. And I have something here. If you're trying to work on it on your machines, you can just uncomment these sections, this piece of code. So what this will do is, once it tokenizes, it looks for whether this is a stop word or not. And there's a isStopWord function which returns a true or a false based on whether a token is a stop word or not. So we can run our information extraction code again. sort the word counts. And doesn't this look much better than what we were getting before, especially the top few words? All right, now what do you think? What is missing? What's good? What's not good? Empty string, yes. That's an edge case that we definitely have to fix. But I see data in Python, which somebody said is a stop word for this specific domain, which should be added to the list of stop words. So, I mean, I encourage you to add it to the list of stop words that we have and see what happens to the code. Did anybody get this running on your machine? One person? Anybody else? Okay, few people. So, any other thoughts? Yeah.
You also have model and models on there. Maybe you could do some lemmatization.
Okay, we have model and models, two versions of the same word in there. So we need to do something about that, different variations of the same word. Okay. All right, so we are not getting the words which are kind of important because they occur fewer times. All right, that's a very good point, and that actually brings me to the next things that I want to talk about, which is most frequent doesn't help us that much intuitively. We need something which is kind of like a ratio of most frequent and least frequent, because least frequent makes some sense. There could be this really niche talk about something that is just one talk, but it's pretty important. And somebody mentioned TF, IDF a little while ago, and that's what we're going to talk about. When we have just raw term frequency, we are making random terms being, the frequency of terms being important without worrying about how many documents they occur in. So the example of these are stop words, but these are also words that don't add a lot of value to our data. In order to combat this, there is this TF IDF, that is take term frequency, and also inverse document frequency. Inverse document frequency is basically this formula. It is the log of n, where n is the total number of documents, divided by the document frequency. So that is, if you have a word, say Python, and if it occurs in all the documents, 1 by df will be n in that case. And in that case, it'll be a really, the IDF ends up being really small. When you multiply the IDF, which is the second part of the function, to TF, we are scaling down the term frequency by the number of documents that something exists in. So now we don't only work with the term frequency or how frequent Python is, we look at how many documents it exists in. The more documents a word exists in, the lower the score goes. Does that make sense? Intuitively? We will talk a little bit more about TF-IDF in just a few slides, where we'll actually go through the math behind it so that intuitively everybody's on the same page. But so far, does it make sense that the number of documents something exists in is inversely proportional to the more documents something exists in, the less valuable it is, right?
Is this a standard formula?
There are some variations for it, but yeah, I mean, usually this is the one that's being used, TF-IDF.
Because the
if it's n, yeah. So you don't want it to have produce not a number or something of that sort. In this particular case, I'm returning a very small number. But definitely, yeah, there are these smoothing parameters and everything for sure. So we can do TF-IDF. There is some code in here which computes the TF-IDF and also the document frequency. Let us go through that.
Does this ever have a dependency on the data set you're studying?
The TF-IDF? What kind of dependency? So the question is, does it have a dependency on the data set we're working with?
Like, for example, there might be some data sets where I would like to have the terms which are the most frequent and then rate them higher than the rest of the terms out there. For example, say tweets and having a particular parameter like terrorism or something like that.
So you want to use TF-IDF when you need to use it. So if you know that frequency is something you care about right now, like tweets, you want to see all the tweets in PyData Seattle and figure out how popular it is as compared to other ones, you won't do TF-IDF. But if you might look at TF-IDF to kind of normalize the data. So if, say, Nordstrom is having 1 million tweets a day as opposed to PyData Seattle, which has 1,000 tweets a day, you want to normalize it based on the total number of overall tweets or something like that. So you will use some kind of a normalizing method. But TF-IDF is probably not right for that particular case. Any other questions so far? All right. So in order to compute TF-IDF, we first need to know the document frequency. We did a word count so far. Then we need to find out the document frequency. That is, given this particular document count, that we are on the ith document, this is the text. How many documents does this particular, these tokens exist in? And that'll give us a DF. And then we compute TF-IDF, which is this particular function. It is the inverse frequency of this given word, document frequency, and the count. So basically, I have split this whole function into, I guess, just to make it a little bit easier, but I don't know if it achieves that purpose. Does it make sense so far that how the computation of TF-IDF? All right, I'll take that as a yes.
The sorting doesn't seem like it works online. I don't know if that's
Sorting doesn't work?
commented online, you know, when you just said it.
Yeah.
It doesn't seem to sort anything like it turned out.
All right, let me get to that in a second, as soon as I get this data. All right, so what do you want to sort? The word count or the document frequency?
Yeah, uncomment line 87. I don't like doesn't error, but it just doesn't seem to sort things.
But you're not returning this value anywhere. Also make sure that you set reverse equals true. So how does this look compared to frequency? And then when we remove the stop words, we're looking at most frequent, we remove the stop words, and then we computed TF, IDF. What do you think? I mean, if you were to go back to your new text stories employer, would you be happy with this result?
It's a good start.
I would be, definitely. So we do see that Spark, Pandas are a couple concepts which we have read about in our, we've seen the titles for these, so in the little pamphlet that we had, so that kind of makes sense. I've seen a few talks about that. There's deep, which I'm guessing is from deep learning, and I know there are a few talks about that as well. So overall, I think it doesn't look bad. And just using TF, IDF for individual words seems to make a lot of sense. The last thing that I kind of wanted to just share is about part of speech. All right. Just a quick comparison between our first thing, which is on the right, where we're just looking at pure frequencies, and on the left, where we are looking at TF, IDF. And you'll see that there's a world of a difference when we know how to use a certain metric, which is relevant in our case, and just use it that way. Part of speech tags, something I touched upon very briefly, and I'll talk a little bit about it, not a lot, is we know that there are these basic parts of speech: nouns, verbs, adjectives, adverbs, prepositions. In NLP, you'll often find taggers, automatic taggers, which tag your data with that. They can parse it so that you have a link to the noun and the verb and what the verb is linking to. But mostly all you need is part of speech tags. This website, and I don't know, I can make the slides available for you, but the Penn Treebank set of part of speech tags is the one that's usually followed by most taggers. And that looks something like this, like noun. Different versions of nouns are NN followed by something, which is NNS is count nouns, which means more than one. So tables. NNP is a proper noun and a collective proper noun, and so on. Similar is verb. There are different types of part of speech tags for the tense of the verb. There are adjectives, superlatives, and the like have different adjective tags, adverbs, prepositions. Here's an example, and this is from the keynote description. Code.org has already helped over 100 million students try computer science. Now, if we just limit our part of speech tagger, and this was taken from the Stanford part of speech tagger. If you go to Stanford Core NLP, you can do an online demo of part of speech tag. In fact, if you would like to do that right now, it'll be really cool for you to check it out. Stanford Core NLP is the Google keyword that you should search for. Okay. If we just limit this by the part of speech tags, that's just nouns, which seems like the most relevant thing for us, we will get code.org and students and computer and science, which seems more relevant than words like already and helped and 100, which is a number, which is cardinal CD. So even if words like try come up pretty high in our TF-IDF list, we don't really care about it because it's not the right part of speech tag for us. You will notice that computer and science are two different tokens. We can do some post-processing to make them a single compound nominal. That's what we call words that kind of belong together, but they are multi-token words like New York Research Institute or Stanford Research Institute or New York Times, which are different tokens, but they kind of go along together. Here is the link for Stanford Core NLP. NLTK is another very popular Python module. One of the issues I found with it is that you have to train a part of speech tagger. They are not allowed. They are not allowed to provide you training data. So you need to have your own training data in order to get a reasonable part of speech output. Stanford Core NLP, on the other hand, although it's Java based, I like it because it has very, very accurate results. It's state of the art. You can get tag data as a preprocessor and then import that data to Python and do all your Python manipulations on that data. So I would highly recommend Stanford Core NLP at this point. Another thing that somebody talked about is getting words in a normalized form. So there were words like that conversation was about model and models. And a lot of people have done two different approaches, stemming and lemmatization. Stemming is basically a form of lemmatization, but it is more of a heuristic to get to lemmatization. What lemmatization achieves is things like am, are, is should all be translated to being or be. Cars should be mapped to car. We want to do something that gets us to this base form so that we don't get multiple forms of that. What stemming does is it's a crude heuristic process. It basically chops off the end of a word to get us a smaller portion of the word, and hopefully it will get us the core word. But the problem is words like marker, like a whiteboard marker, it'll remove the ER from it and it'll become mark, which might be not what you want because marker is a noun and you don't want to chunk ER from that noun. Lemmatization, on the other hand, it uses a huge vocabulary, and first thing it does is this is a noun of type this, so you can only remove the count from it, that is S. Cars, you remove the S from nouns. That's one of the patterns that you have for nouns. So it's a more traditional NLP people love doing this because they want the actual meaning of the word to be around. Non-traditional people who have a lot of data at their disposal choose to do stemming because it's quicker and you end up getting reasonably good results if you have a lot of data. So it's up to you which option you prefer. Lemmatization will just help you keep the actual meaning of the word in the base form, if that makes sense. Now, I won't go through experiments using the part of speech, but if you want to talk about it, I'd like to talk about what would improve if we use just NPs, or that's noun phrases, or just nouns. Any thoughts? Yeah, it will automatically remove a lot of stop words, a lot of words that we're not interested in. Verbs, acquires, talking about.
I saw you and your.
So going back, yeah, you and your, using TF-IDF, we get you and your, both of them, which we don't care about too much. And it, hopefully using some kind of lemmatizer, we might just get you. If we use NPs, we might end up getting, we won't get this because these are pronouns and they are not nouns, so we don't get this data at all. Anything else? Smaller number of words, yes, definitely. We won't have as many candidates. We'll have very few candidates that we care about, so we'll have much more intelligent metrics that we can do on it.
Is there any lemmatization module that you are in Python?
I haven't come across anything. There is stemming in, so the question is there a lemmatization module in Python? I haven't come across anything. Yes? There's a tokenizer in NLTK, which one can use, but there aren't lemmatizers in there. Okay, so to recap, we looked at tokenizers, cleaning up of data using UniDecode and modules like that, word frequencies, word vectors, TF-IDF, part of speech tags, lemmatization, and stemming. So we did some information extraction, basically extracting some kind of information from unstructured text. And I know at this point you're thinking this was pretty basic. This is not information extraction, but this is exactly what it is. There are so many other ways of extracting information. Like there was this woman who was doing experiments on getting different types of a given set, so colors such as red and blue. And what she did is she entered red and blue and basically giving two examples to Google. And Google went ahead and said, well, every time I see red and blue, I see green or I see purple. So we can extract information from unstructured text. That's this person discovered different types of colors, different kinds of words which belong to the class colors using this simple Google experiment. This other person did the same thing for cars, cars such as Toyota, Honda, Mazda, and Mazda and BMW. You can also do this to find verbs. So how are two different words related? Microsoft bought Faircast. If you type it into Google, you'll get other words like Microsoft snapped up Faircast, acquired the startup Faircast. So there are several ways in which you can represent the same information. So here you're getting synonyms of the same verb, which is bought. Any questions so far? All right. So this is basically information extraction in as brief of a talk as I can do. It's very simple, it's very intuitive, and you need to find the right metric that you need to use for your specific task. So you go to your bosses and they say, yeah, very cool, this is nice. But there's one more thing I need. If I type in this term, can you show me all the talks about it? Or can you show me the talk that's most relevant? And it sounds like a hard problem. I'll leave you alone. This will probably take several weeks. So you're sitting in your cubicle and thinking, all right, now what? Any ideas?
What's the idea based on TF-IDF?
All right. Something based on TF-IDF. Okay. Sorry? Cosine similarity. Okay. Bag of words. All right. Now let's go through plenty of suggestions. Something based on TF-IDF, cosine similarity. Now, when you think, is anybody familiar with cosine similarity? I know, except the person who's there's a few people. What would you apply cosine similarity on? Features. So, what happened? Okay. So, one of the ways I like to think is thinking from the very basics. What we want is basically, given a keyword, we want to find out which document has a match with that keyword. Sorry? Just a simple search index. I mean, that's one of the basic things that you can do. You can just do a simple keyword match and get what you need. And this is interesting because that's how our mind works. We want to get to a really complex problem, and we want to apply something really complex to this, but maybe we can get to this using a simple inverted index where we have all the words that belong to different documents, and given a word, we retrieve all the documents that belong to that given word. Does that make sense? So for instance, if somebody types in Spark, and we have just 2 talks about Spark, we have this dictionary that returns those two talks to the user. And there's no complicated stuff that the user has to do. So what I'm trying to say is that this is a simple keyword match problem. It doesn't have to be complex. And as data scientists, we end up taking the more complex route as opposed to taking the simplest route there. Now, if the phrase that was given to you was not as simple as a single keyword, that's when we would need something more complex. So for instance, if you're given a phrase as Spark with data science, you might want to look at vectors of words and do some kind of a fuzzy match, in which case these would be pretty useful. So the fairy godmother says, fancy algorithms will help you build products rapidly, but you need to know how those algorithms work to apply them well and know whether it is actually relevant to your task. This specific thing is pretty similar to information retrieval. And I'll show an example about the vector space model using TF-IDF that somebody talked about, that somebody just said out loud, and cosine similarity, which somebody out there said. And computing the similarity between a phrase and a document, where the phrase is much more complex and where we need something which is more complex than a simple keyword match using an inverted index. So the theory is something like this. You create a vector for each of the pages. So we have this long vector, which is pretty sparse, and it has D1, D2 are the document numbers, and it has all of these numbers representing the index of the word. So this could be word number 1, 2, and the presence or absence of it is determined by whether there's a number there or if there's a 0. And then we find the similarity between a document and the phrase that's input. The phrase would be probably fewer words as opposed to the entire document. And the page with the highest similarity wins. So a page would probably not have all the words in the entire English vocabulary. So it's going to be a pretty sparse matrix. But if we have the vector with the index of each of the words, we can assign values to it. So for instance, this is a vector document 1, which has the word A in it. It has the word bug in it 6 times maybe, and some other words, some other frequency of times. We can make this more complex by making each of these values, instead of the frequency, as I've shown here, the TF-IDF of that. And then once we have a vector, given 2 vectors, you can easily compute the similarity. And there is this cool way of doing it, which is using dot product. So this is actually what the dot product is. If you look at the information retrieval book on the Stanford website, they do a really nice job in explaining in much more detail about what the dot product is. But basically, it is the cosine of the angle between 2 vectors. So if D1 and D2 are 2 vectors, we want to measure the cosine of the angle. The larger the cosine, the less similar they are. The smaller the value, the smaller the value, the less similar they are. The larger the value, the more similar they are. So what we do intuitively is convert each document into a vector where each value, each index is represented by a word. So index 0 is data, index 1 is Python, and so on. And the value is the TF-IDF of the word in the document. If the word does not exist in the document, then set the value to 0. I'm using a very, very simple Boolean vector. So there are 3 different vectors for 3 different documents. The first one, if you just eyeball it, it's pretty data science stuff. Data science, it has data in Python, NLP, Theno, and none of the other words like banana, or elephant, tea. The second one talks a little bit about apples and bananas and NLP. And the third one is, again, all over the place. It has data science, and it also has apples and bananas. And we want to figure out which vector is most similar to vector 1. Is everyone with me so far? Any questions? All right, so we compute similarity between V1 and V2, and that is by the dot product, which is you first, the numerator is multiplication of these values, individual values, and the denominator is the magnitude of each one of them, which is the square root of the square root of the squares of each of these values. So going down to the nitty-gritty, it's basically 1 times 0 plus 1 times 0 and all of that stuff. And the denominator is the square root of 1 squared plus 1 squared plus 1 squared plus 1 squared times this value.
And so the length of your vector is just the superset of all words in every document?
Yes. Length of the vectors is basically the superset of all words in the document, in all the documents. So you have to have a set vocabulary before you try to create a vector for each document. So the similarity between document 1 and document 2 is 0.289, which kind of makes sense because document 2 doesn't have data in Python, but it has words like apple and banana. When we look at document 1 with document 3, we get, in using the similar metric, we get 0.817, which is a higher similarity, and which tells us that, you know, intuitively that's what we thought, that document 1 and document 3 are probably talking about the same thing just because they covered similar concepts. But now we show that mathematically that is the case as well, that document 1 and document 3 are very similar. So you can actually go ahead and implement this if you want to. So one of the first things you want to do is build the search model, where the first thing you would do is have an index, figure out how many documents you have, what's the total vocabulary, and that you can only do by parsing the entire corpus, entire data set in its entirety. Then, once you have all the words, and you have the count of all the words, and the document frequency, that is, how many words are in each document, or which words belong to which document, we can compute the inverse document frequency. Then we initialize, I'm using NumPy for this particular case. I didn't want to, I wanted to use simple lists and everything, but it's just much more simple to do computations using NumPy as opposed to simple lists, and it's much more faster, so I highly recommend it. The next thing that we want to do is compute an index. So if you remember from my slides, each position in the vector belongs to a specific word. So we want to make sure that we don't change that for different documents. We want to retain the same indexes. And then finally, we'll compute the TF-IDF for each document. So you'll notice that we are using the same IDF. You compute the IDF once, that is, for each and every document you have, for each and every word, you have the inverse document frequency. And then, given a new document, we compute the inverse document frequency for each word in the new document using the word frequency from that document. So if the word Python occurs in document 1 3 times and document 5 29 times, we will compute the weight of Python, which is the TF times IDF, for those documents. So in the first document, it'll be 3 times the IDF, and in the fifth document, it'll be 29 times the IDF. So you see that the frequency of the number of times a word is in a document has a huge impact on the weight of that particular word in the vector. Does that make sense? Yes.
How do you normalize by the length of the document?
Well, that's what the question is. How do you normalize by the length of the document? That's what the log was, where hang on, you do not actually in this particular case. You're not normalizing by the length of the document.
You're simply comparing two vectors, right?
Yeah.
It's just that one document's 10,000 words, the other document's 300 words. Then the TF-IDF isn't a great comparison because it's just more words.
So you can normalize your vectors based on how the distribution occurs. And that's one of the things that you can do. In this particular case, because the document lengths are pretty similar, I haven't done any of that. But yes, that's a very good question.
I think while calculating the cosine similarity, like vector 1 dot vector 2, and in the denominator we are taking the modulus of the vectors. So in that way we are normalizing the document itself.
That's a fair point. Well, cosine similarity, that's one of the reasons that we use that instead of the magnitude of the vectors, because it takes into account the length of the vectors, and when you actually do the similarity, it just looks at the angle rather than the length of the vectors. So we don't look at how far apart they are, just at the angle between them. So if there are two vectors where one is, the magnitude of one is really large, the other is really small, but they are on the same angle, they'll have a very high cosine similarity or similarity of 1, irrespective of the size of the documents. Thank you for pointing that out.
Which makes sense, because if you've got one document that's a subset of a much bigger document, that's going to be the highest match in your cosine square.
Right, yes. So the comment was, which makes sense, if one document is a subset of another document, there will be a very good match between document 1 and document 2, because one is a subset of the other, so it has to have a highest match, which is what cosine similarity will give us.
And even though the cosine might be lower because it's a different size, it's going to be a higher number than another random document would be, obviously.
Now the size, because we are normalizing by the magnitude of the vector. So if you go back to the formula of,
If you look at the cosine formula, you're dividing by the length of the two vectors. That's why you're normalizing it. So they all become unit vectors.
yes,
So it's a unit vector, then the set length doesn't matter. Only the angle matters. So
The-
they become unit vectors.
exactly. So we are dividing them. The dot product is divided by the magnitude of each of them. So if one vector is really large and the other vector is really small, we're still dividing it by the size of the vector. So each of the vectors becomes, as somebody pointed out, it becomes unit vectors, and we do not discriminate based on the length of the vector. Any other questions? All right, so we can go ahead and actually work with our search model. What I've written so far is basically a system that computes a model, which is basically a large NumPy array, the IDF, the word to ID, and the number of documents, and it builds a search model. And then there is this search function, which, given a phrase, the IDF, the word to ID, number of documents, and the model, it'll actually search the model and produce the document ID with the highest similarity. Oh. All right, so we have some kind of a model. Let's see how it looks. As expected, it's probably really a large number of rows. So it's 79 rows, which makes sense because we have 79 documents. Each row has 2527 columns, which means that the vocabulary size in this particular case is 2527. Each row kind of looks like this, where we have numbers, each word represented by numbers. This other thing that we can look at is word to ID, where each word is given an ID, subsequent has an ID of 1015. So column 1015 in our model represents the word subsequent for all the different documents. Does that make sense? Anything else that you want to look at? So we have IDF, number of documents in the model. Okay. The next thing we can do is we can actually search. Any search suggestions? I'm just putting some random words in there. So if you're running the code with me, please make sure that you have, when you're returning it, make sure that you are using word to index instead of word to ID, because that's the parameter that's being passed to the search function. I haven't talked about the dot product. This is what the dot product looks like. Given two vectors, we compute the product of each of the indexes. So that is, in position 1, if we have P and Q, we find the sum of the product of that and we add that up. And the denominator is the square root of the squares of each of the indices there. All right, so pandas, Python, NLP tells us that number 76 is probably most relevant. If we change this up with just pandas, we'll probably get something else. Number 30. And again, number 30. So if we go back to I am not able to increase the size of this. But if you go back, if you look at your own versions of this data, yes.
For calculating cosine similarity,
Yeah.
you are dividing by the square root of the square of the magnitude.
Yes.
But since we cannot have negative values there, what's the point?
Yes. So, to handle that particular case, so, well,
You can just write the magnitude y square and square root it.
oh, so, okay, sorry, I misunderstood the question. So the question is that why are we finding the sum, the square root? I mean, what's the question again for?
Squaring and then square root.
So that's the formula to actually convert a vector into a unit vector.
That's more useful when you have negative, so
The,
negative values too. So the cosine similarity can be negative, but since the number of, we cannot have negative count of any vector here, you won't have negative cosine similarity.
right. Well, but we're still kind of going by the definition of cosine similarity. So that's basically the length of the vector. So you have a fair point that it's, I mean, when there's negative things, we can actually account for negatives, but in the end of the day, we still are looking at the magnitude of the vector. So this is the way we can actually compute what's the actual magnitude of it.
With the given formula of the TF IDF, I don't think the can be.
Yes, and so I was telling you about the TF-IDF and how in IDF conversion, in IDF computation, if the value is less than or equal to 0, we're returning a very, very small number. Yes, we can totally do that too. We can normalize the denominator by adding 1 to it so that we don't have any issues like that. All right, any other search terms that you want to type?
Can you put some word which is not there in the process?
Okay, I haven't handled those edge cases.
The reason being because it will fail because you have defined IDF in a way like n by IDF. If the term will not lie, the log will become like log of n.
it probably will fail because I haven't handled those cases. But you're welcome to do that and issue a pull request on the repo. All right. Well, I don't think there are any more suggestions. If there are, feel free to speak up. Any thoughts or suggestions on what we did so far on TF-IDF and search? Sorry? So yes, the question is how do you handle polysemy where a same word means two different things. So to talk about that, how does Google handle polysemy? How does Google handle, if you type in rock, it might give you words like mortar or cement, and it will also give you search results for a jazz concert or a rock concert close by. So you'll get search pages similar to both of these concepts. And so far, it's been up to the user to figure out which one are they interested in. So computers figuring out different meanings is entirely based on context. So if you provide more information like rock concerts, a computer would know or a model would know that, oh, rock and concerts, so it's most likely that this person is interested in rock concerts. They might also be interested in heavy metal concerts and other things like that, which is related to music. However, if you say that small rocks or pebbles, rocks and pebbles, if you type in something like that, it'll give you completely different results. So it's more context which will help you figure out polysemy.
I don't know whether it will be a valid question or not.
So when you type in an ambiguous query, you will probably get Google has definitely much more than TF-IDF. It'll look at obviously look at your previous search results and everything. But if it's super ambiguous and if it's nothing that Google can help you with, it'll provide you all different kinds of results and also say, did you mean this particular thing? Or it'll have other suggestions where people have typed in queries which have more meaningful results. So it'll give you context. It'll give you things which you can use to make your search query much more interesting. This kind of is going into this whole area of query expansion, where you want to expand your query into something much more meaningful, as opposed to something really simple. So if you're interested in that, feel free to look up query expansion. Any other questions?
So let's suppose that I'm doing some kind of dimensional.
I'm sorry, I can't hear you too well.
Let's suppose that I do some kind of
Dimensionality
reduction, meaning
Dimensionality
somebody
reduction, okay.
somebody to NSI. Let's suppose I do some kind of 1960 analysis. So I'm doing the dimensionality reduction, and I need to use some kind of listening disaggregation. How do I go about it?
All right, the question is, you are applying LSA or some kind of a topic, LSI, some kind of a topic modeling algorithm, and you want to figure out polysemy, you want to solve polysemy. This is not quite related to the talk, but you want to solve the problem of polysemy. How will you do that? My thoughts, just randomly, with this question is I would use something like nearest neighbors to see what is the context around a specific vector in order to figure out which other concepts it's close to, and then clustering concepts based on that. So it's sort of a second step to LSI. You are modeling your topics, but then you're also modeling those individual concepts to figure out which topics are clusters. Does that answer your question? Any other questions?
By applying like cosine similarity, we got some numbers.
Yeah.
Okay, like these are like one-liners, so we can see okay, it's matching, but it's not matching. But is there any standard thing through which we measure like how accurate our results are?
The question is, very good question. The question is that using cosine similarity, we get some kind of metric, and we are getting a document which our phrase is most related to. But how do we evaluate it? That's a very good question. And information retrieval, it is a very hard question because we don't know what the final answer is. We could, maybe the query is ambiguous that we don't know that it's, one person means rock concert and the other person means rock as a pebble. One of the things that people usually do in terms of information retrieval is have some unseen test data, which is kind of what similar to machine learning test, where we create a model and then we see how accurate our system is on this dummy data, which is unseen, and based on that kind of improve the model but not train on that specific model. Another thing you can do is take the Google is God approach, have a bunch of keywords, extract the top 10 Google results, store them up, and see whether your model achieves what Google is achieving, which is also one of the things people have been working with.
We can also use semi-supervised learning, meaning somewhere between supervised and unsupervised.
So the comment is you can also use semi-supervised learning, have supervised and unsupervised together to come up with something. All right, so you just did information retrieval. You developed something. Yes, question.
So when it will be helpful to use n-gram instead of using just one?
Question is, when is it useful to use n-grams as opposed to using single grams or tokens? The reason why I've made it very simple here is just because it's easier to understand. It's easier to compute. Computing n-grams is adds an additional layer of computation, which we would like. I mean, ideally, we do not want anything like machine and learning to be two separate concepts. We want it to be one concept. So it's always good if you have the bandwidth, if you have the resources, work with n-grams so that you actually have the actual representation of what the n-gram is, what the word is, you know. And a lot of people have different ways of doing it. Sometimes what is done is that when you compute these n-grams, you make it into a pseudo token where you join those words with an underscore. So a system will think that it's a single token, whereas your post-processor or pre-processor has already determined that it's two tokens joined together. So does that answer your question? So it's always good to use n-grams when you can, bottom line. Any other questions? Yes.
Again, I don't know if that's relevant. What if it, let's say I'm searching and I type the word wrong, like PYTHO, instead of PYTHO and
The question is, what if there are spelling errors or basically out of vocabulary words? What does your system do? It's again an edge case which your system should handle.
I'm not talking about the edge case, I'm talking about the search results in general. Like many times when Google types some wrong words, that is, in spite of that we get the correct.
Yes, Google has language models in it where it knows that what if you probably meant so and so word, because the possibility of this word occurring is very little. There is a very, very simple 100-line spelling corrector which you can actually write in Python, and I'm unfortunately not going to cover it here, but you can. It's a very, very simple spell corrector that could be plugged into the search engine and check for misspellings. What I'm trying to say in terms of edge case, and probably edge case was not the right word, it's a different component. It is like if there's a word which is out of vocabulary, what do? Do you find other documents and index them? Or do you see whether this word is actually not a word at all? You need to change this word into something else. Is this similar to some other word? So that's a different, that's definitely an add-on. I mean, if you're building an information retrieval engine from scratch, you want to make sure that those cases are handled, but it is not core of the actual retrieval process. It's actually the query step that you have to figure out that the query is relevant, query is accurate. Does that make sense? Any other questions? Okay, so we just did search, and you went back to your company and they are like, wow, this is awesome, really nice. But now it's a little bit of a stressful situation for you because you delivered a lot of things really quickly and you want to learn new things fast. So what's new in the whole area of NLP? And that's deep learning. And one type of it, which is sort of deep learning but not quite, it's word-to-vec, which is what I'm going to talk about. It's basically this big model. I'm sorry, did somebody have a question? It's basically this big model that can actually it knows semantics. So if you have one of the classic example of word-to-vec is that you said the vector for king minus man plus woman, and it said, oh, that's queen. So it knows the semantics, the actual meaning of what king is. And when you subtract the vector for man and add the vector for woman, it'll give you queen. And similar words like duchess and words like that. If you want to run word-to-vec, you can get it from gensim, which is a Python module. Sudo pip install gensim should do it. Word-to-vec tool takes a text corpus as input and produces word vectors as output. And there's always that evaluation question. How do you evaluate whether your model is right? Usually, one of the simplest ways is eyeballing the data. So what are the closest words given a given word? So if you enter France and you get Spain and Belgium and Netherlands and Italy, it's probably doing the right thing. It's learning what it's supposed to learn. It has two different approaches, and I'm going to get into a little bit of detail. and that is CBOW, which is predicting the probability of the context given a word. So if you have 5 words, one word would, the presence of one word would predict the presence of other words. The other is skipped gram, where you're predicting the probability of a given word given the context. So in skipgram, you have several words which predict the central word, and then you have some sort of back propagation, that is the errors that are produced with these functions are brought back to the original matrix. And I'm not going to get into too much detail because this is like a couple hours in itself, but it's just a very rough idea of what it means. CBOW, where we are predicting the context. And then again, it has a back propagation algorithm which takes back the errors and it keeps tuning those weights till we reach some number of iterations. It uses gradient descent, so as soon as it thinks that as soon as either we're out of data or it thinks that we found an optimal position to stop, it'll train. So if you want to run it at your end, there's a very good implementation in GenSim. Download and install GenSim and train a model. I've done some work in making this online. So the current GenSim implementation just takes a list of words, a list of documents, trains on it, and then you cannot change the total number of words in the vocabulary. That's one of the updates that I've made. There's a PR open right now, but it will add new words to the vocabulary, and it'll basically train it such that the new words are semantically located in the right position. And if you want, I have a quick demo for that. Or maybe not. Okay, I haven't seen this error before, so I'm not entirely sure what's happening. If you're interested in learning more about this, though, online learning of word2vec, I've written a blog post about it with evaluation and other things. So you can just go to my website, rutumulkar.com, and it has this approach of what I did for online learning of word2vec. So basically, I created this corpus in 2 pieces. The first one had all the words related to king and a lot of other words. The second corpus had added a new word called queen. And the idea was that we want queen, the vectors for queen, to be similar to that of king. So out here, if you see this, I train the model with some sentences, and then I compute the similarity between king and duke. and I get a high similarity, 0.68, which means we want queen to be around the same similarity when we learn about queen. Then I look for similarity between king and queen, and it says key error, there's no queen, which makes sense because the model, the actual document, the list of documents in text 8 did not have queen in it. Then I introduce this new vocabulary, which has text 8 queen, so all the words related to queen, about 1,000 sentences, and then I evaluate the model again, and I find the similarity between king and duke, it's 0.55, and king and queen is 0.64, which means that when we introduce this new word queen, the model is learning the vocabulary, the vector for queen, and it's placing it in the right space, as it should. So yeah, I just wanted to show you a demo for that, but unfortunately, it's not quite working, so my apologies. But feel free to download GenSim and experiment with Word2Vec. You cannot do online training right now, but you can learn the semantic meanings of words, and you can also use pre-trained models that you can find online on the Word2Vec website and run arithmetic on vectors. So we just did some deep learning. And that's coming to the end of my talk. We talked about information extraction and information retrieval, Word2Vec. Basically, NLP is extremely intuitive. You need to know what you're looking for before you apply any algorithm. Once you know what you are expecting, you can figure out what approach is best for you. If you have any other questions, feel free to email me or tweet about me. And that's it. Hope you enjoyed this talk.